All right. How you guys doing? Doing okay? So if you happen to notice, last time we had some internet issues. Probably noticing right now our Wi-Fi is not great. So the recording from last lecture lasted 20 minutes and then was gone. I didn't notice that while I was recording or while I was streaming. So this time and in the future, I'm going to aim to record in addition to putting it live so I can upload it. In the meantime, you have the 20-minute video bit of the lecture from last time, and on Moodle I've put a link to last time I taught the equivalent of that lecture. Should be pretty close. I do try to review and might have been in a different spot during the course or something a little bit, but it should be the same content, approximately. Okay, so that's available to you if you missed it or need it. And I'll try to make this specific lecture available as usual. It looks like it's okay right now. It did take my laptop a couple minutes, and the signal strength is kind of going up and down, so we'll see. Okay, so you've got the attendance here. Starting next week, these will be kind of included into your grades eventually. Again, this is kind of just practicing, and I have to file something with LSU to say, hey, XYZ people were here, I confirm. Okay, so that's the purpose right now. Anybody need another moment for this? Okay, so go ahead and do that. Today we're going to pick up where we left off with the development of a mass balance equation. We kind of cut short a little bit last time on that, so I'm going to give us a moment to take a look at not just the batch reactions, but also what happens if we have some flow as well. So practicing connecting the reactions with the reactor itself in order to derive some sort of a mass balance equation is what we say, that you'll often see problems tell you to find a solution for. And it's like, well, you didn't specify an equation or anything. What do you mean find a solution? What we're referring to whenever you see something like that is finding the solution based on the mathematical principle that we have a conservation of mass, okay? And then from there, you could solve for the time it takes or for the amount of chlorine it takes or something like that. Okay, so with that, I'm going to come back to our slides where we left off. So we were talking about the mass balance for a batch case. I gave you a chance to take a look at this, begin deriving it. We wrote all these notes and ultimately said we can find a solution for the concentration of a given substance as a function of time. Now, what you'll note is you could solve this for time instead of concentration. Maybe you have concentration, you just need to know how much time it takes. In fact, many times that'll be the case. We want to target a specific endpoint concentration. I don't want any more than this number of viruses in my water per liter because I know that'll be protective of health. Therefore, how much time does it take? Okay, so sometimes we will take a mass balance and solve it for something else other than C. Perhaps we'll solve for the time. We could solve for the rate constant. How efficient does this reaction have to be? Or maybe we know everything about the reaction except we don't know the constant, so we could solve for the constant. So all that to say we can develop this mass balance relationship and then use it for whatever piece of information we need. Okay? And sometimes we'll have to do that in order to solve for something else, to apply it. So these mass balance equations are going to be a lot more useful than just solve for C, okay? Although that is something we can do. All right, so we did the batch case, and as I told you, that's approximately the same as the plug flow case, as assuming we take it like a batch on a conveyor belt, and it pours out at the end, okay? Now, it gets a little more complicated if we do a continuously stirred tank reactor. And this one, the CSTR, remember we have some container, looks a lot like a batch container because it's well mixed, but here we have a flow going in and a flow going out. So let's say we have a QC in, so QC naught, and a Q and a C going out. Now I always label it with a Q and a C next to each other. I'm putting a comma there to say, hey, we have a Q and we have a C, and our reactor has some volume. A lot of times when we put the Q and the C for the input or output rate terms, it'll be Q times C. But just noting it here, I'm putting a comma there because I'm just saying we have both of those. So don't get confused by how I'm writing that. I could also write this as Q and a C naught, just saying that those are there. All right, so given that, take a moment and see if you can do the same thing for this zero order decay reaction. Okay, find a mass balance equation. Let's go ahead one more time to solve for C as a function of time, or as a function of the rest of the parameters. To solve for C with whatever equation you get out of this, and we will make a steady state assumption. But you could also check to see if what it would feel like to begin solving it without the steady state assumption. So feel free to take that, carry that along for a moment and see what would happen. How are you feeling? Getting somewhere? Getting confused? A little confusion? Some people okay, maybe? Feel like you got an answer? Or getting an answer? Not quite? All right. So hopefully you remember that our overall mass balance we can describe as the accumulation of this stuff, the C, in our reactor is going to be equal to what's coming in minus what's going out, plus whatever kind of reaction we have happening. So in this case, we said we have a zero order decay reaction inside this CSTR. So it's a container, well mixed, flow going in, flow going out. So we can write the accumulation term as V times the change in C over time. So the change of the C per volume in that volume. Okay, that's our mass per time accumulation rate. With this steady state assumption, we'll say that equals 0. But just to write it out up front, we'll say V dc dt equals the input rate being what's flowing in. That's our flow rate Q times the influent concentration C naught. Minus the output rate, that's again the same flow rate, times C, the concentration leaving. Now that C is also the same as the C that's inside here. So we have C inside the reactor. If I drew it larger, I would make it look kind of like this. It's a well-mixed reactor. We have some volume in here and also some concentration C. Okay, so that's just expanding that a little bigger. I'm going to erase this in a minute so I can make room for the other side. But for the moment, this is what we're looking at. A QC leaving and a Q and a C naught coming in. All right, so those are our flow terms, the obvious parts. Then we have the reaction term. And this reaction is happening inside the context of the volume, so we need a volume term there. So this will be, I put plus the reaction, so plus V times however C is reacting, the R of C. Now here's where you need to remember, and I have a reminder right here, that for a zero order decay reaction, we'll add a negative in there to say we're decreasing. And because it's a zero order, that means the way we describe this reaction is the rate constant times the concentration to the nth power, where nth is the reaction order. So it's a zeroth order, so this is C to the 0. That means this is essentially minus K. So when we rewrite this, we'll say this is equal to QC naught minus QC plus a negative V times K. C to the 0 power is 1, so I'm just going to write it as 1. Okay? Yeah?
For this problem, just why are we assuming that Q in and Q out are equal?
I didn't say that they're equal. The Q itself, QC naught is not necessarily equal to QC. The Q's are equal because we have we're going to assume we're not gaining or losing water inside the system. So if our water stays at a constant volume, then the Q's have to equal because there's only one Q going in and one Q going out. So great question, and I'm sorry I misheard it at first or misunderstood. So the Q's will almost always be equal. If we just have one going in and one going out, I'm never going to give you a problem where the volume of our reactor itself is changing, or we're having some unknown source of water leaving or coming in. You can imagine that could be a pretty challenging situation if you have a leaky reactor and you're losing volume somewhere, then your whole steady state assumption goes out the window and your math goes out the window too. So there would be challenges if Q's did not add up nicely. We're not going to do that. And in most cases, it makes sense if we have, yeah. So the VDC is like the accumulation rate? Yeah, so the accumulation rate, we are always going to write as in that volume, the change of concentration over time. A lot of times we'll set it to 0 with a steady state assumption. But even if we look back from last time in the batch case, that's exactly how we started, saying, okay, in that volume in the batch situation, how is that concentration changing over time? V times dc over dt. Okay, does this part make sense so far? All right, so now we will say at steady state. Well, let me just take a moment to say, if we kept this at v dc dt, you can see we have some sort of integration coming, right? We'll have to perhaps separate c and figure that out, do a little bit of calculus, and in a zero order, it should turn out to be quite simple. But it's even more simple if we're at steady state. So steady state means that even if we're changing the amount of C in the water, the total mass of C in our reactor is staying steady. We've been doing the same process for some time, and so we're not accumulating or increasing or decreasing the total amount of C in our reactor. So that means V dc dt equals 0 because there's no change over time in C within that control volume that we defined. Yeah.
Can you just assume it's going to be 0 every time?
If we say it's steady state, yes. Sorry, I cut you off.
Yeah, no, not.
Okay, yeah, if you see steady state, that's exactly what it means. Always that's what it means. So then the only case to watch out for is if it's not steady state, or if we have a batch reactor, it can't be at steady state if there's some net reaction happening. You're going to have that there. But this means we can simplify and say 0 equals QC naught minus QC minus VK. So we were tasked to solve for C, so we can add QC to both sides. We'll get QC equals QC naught minus VK. Divide everything by Q, and we will get C equals C naught minus V over Q times K. And what is V over Q? Heard some of it? Okay. This is theta, our hydraulic residence time, right? So another way to write this would be to say this is C naught, bless you, minus theta K. It's our hydraulic residence time, and we define that as volume over flow rate. Okay. Does that make sense? Okay. If I asked you to do this with a growth rate, you think you could do it? Zero order growth? It's basically the same thing, you just have a positive there, right? Okay, so you'd flip some signs and do that. All right, how about this first order decay? Why don't you go ahead and give that a shot? We'll again assume it's steady state. So I'll set the problem up with you. And one key I hope that you're seeing here is the importance of putting in the right terms. The reaction term, for example, has to go in here, and that's kind of how we're navigating this. Got an answer? Close to an answer? Just a little bit of algebra from here where I've got it. Is this process making some sense to you? Kind of getting it? Okay, this is fundamental to the entire class. So if you can master this stuff, that'll be very good news for you on all the problems in the future, because this is the basis for almost all of the class. This type of, okay, here's some reaction, here's some context for it, let me assemble this mass balance to put things in the place that we need them. So we'll go ahead and solve for C here. We notice that we've got two terms with C in it. So I'm going to get them on one side by adding them both to both sides of the equation. And I'll go ahead and separate. We'll factor out the C and get Q plus VK equals Q C naught. Now, one thing that you might notice is we could have divided everything by Q, kind of simplify things a little bit. And maybe we'll go ahead and do that. We'll just divide everything by Q here. Could have done that in a previous step. But if we do that right now, we'll get C times 1 plus, here's that theta again because it's V over Q. Theta K equals C naught. You don't have to divide by the Q there. You could do it later. You could do it earlier. You don't have to divide by it at all. I just find it makes it a little simpler. So then we can get C equals C naught over 1 plus theta K. All right? So in some sense, this would be the solution to the mass balance, or rather we have derived an equation for C as a function of the hydraulic residence time, the rate constant, and our initial starting condition. Now, a lot of times we're actually going to be interested in C over C naught. So how much do we have there compared to how much we started with? Sometimes, in the case of when we look at flocculation, we will be interested in C naught over C. How many of the old particles are there per bigger particle? So depending on what we need from a problem, like I said earlier, we may be changing this. So if we were to derive this for C over C naught, for example, this would simply look like 1 over 1 plus theta K. All right? So you can see we can do a lot. We can move these around, and we really will see this one a lot. We're even going to see the inverse of it sometimes based on what we need. Okay? Good on that? And hopefully you can see how you could approach this if you had to do a first order growth reaction or even a second order reaction. Assuming we're at steady state, many times that still is reasonably simple. You can also imagine that if we were not at steady state and we had a second order, we just need some more calculus, right, to remember how to deal with the integration of 1 over c squared dc or something like that. You know, there are tools for it, but we're not going to bother you too much with it. Okay, so let's make sure you can do this. Here's an example from our book. We'll spend a few minutes on this, and then we'll get into the chemistry refresher. So consider a 10 by 10 to the 6 cubic meter lake fed by a polluted stream having a flow rate of 5 cubic meters per second, and pollution concentration equal to 10 milligrams per liter. So it's sort of a generic pollution we're just going to describe. We'll actually talk more about this when we get to wastewater. This is going to be kind of a BOD type of a thing, but for now it's just some pollution. There is also a sewage outfall that discharges half a cubic meter per second of wastewater having a pollutant concentration of 100 milligrams per liter. And sewage wastes have a decay rate coefficient of 0.2 per day. Assuming that the pollutant is completely mixed in the lake, assuming no evaporation or other water losses or gains, to answer that question from earlier, is the water changing? Evaporation could certainly change it, right? So it's a really good question, but again, we're going to keep it a little bit straightforward here. We're not seeping water into the ground or evaporating it or anything like that. Find the steady state pollutant concentration in the lake. So you'll see we've been given a lot of hints along the way for all the different things we've talked about to set up a mass balance. So the problem is tossing in little bits and pieces here. Okay, assume steady state. Here's a reaction rate. It's well mixed. It's covering a lot of these pieces, but you're going to have to be tuned in to recognize, okay, this is telling us how we can assemble the mass balance. So take 2 minutes to read this and start thinking about how to set it up. Then I'm going to interrupt you and highlight a few things that are really important. So do for yourself. See if you can highlight pieces of information that you know like are standing out to you that are important. And then I'll do that with you, and then I'll give you a few more minutes, and we'll solve it. All right, so what do you think about the reactor type itself? What kind of reactor are we dealing with? Yeah, CSTR, because we have inputs, it's well mixed, and we have outputs. Now, I will note that we have 2 different inputs and 1 output, so we do need to manage that, but even though that's not how we've written up the mass balances so far, we've been doing a very generic 1 input, 1 output. It's no problem to have more than 1 input rate. Right, so when we do our accumulation term, equal to, so accumulation is equal to the inputs minus the outputs, we can have more than 1. So in this case, we'll have 2 of those, plus a reaction term. Right? So we'll have more than 1 input, no problem. All right, what do we know about the reaction itself? Where we're given a rate constant. The rate constant is 0.2, and the units were per day. What order of a reaction is that? Okay, a few of you remembering. Some of you may be not remembering, but I'll remind you, we should know this is a first order reaction, and the reason for that is because when we say our reaction, which is the change in concentration over time, if this is, let's say it's a decay reaction, so it will have a negative here, it's going to be K times C to the nth power, and we can find N if we know something about the units. Well, on the left side, the units have to be something like milligrams per liter per time. We'll give that as per second for now. Then that means the right side has to have the same as well. So if K is 1 over time, in this case 1 over days, then the concentration has to be in, if K is 1 over days and then the c to the n power has to give us units of concentration because we've got the milligrams per liter here. So we have to make this match one way or the other, so n has to be 1 in order to satisfy the left side here. Okay, now, of course, we're given per days. We might be trying to solve in per second, or maybe we need to just say this is going to be per day as our dt. We'll just double check that as we're solving the problem, our units are matching, okay? So we might have to do a unit conversion, just kind of heads up, because we have some flow rates in seconds. We have a reaction rate constant in days. Just, we'll keep that in mind. But we do know it's first order, right? Okay, so that's a couple hints already. We know it's a first order. That's important because just like we were doing a moment ago, how we derive our mass balance and the equation that we get at the end of the day depends on that, right? It depends on whether or not that C is showing up right here. That'll change the rest of the problem. Okay, so we've got first order. We know that because of the units. We have a CSTR because that's how this thing was described. And we were also told this is a steady state concentration. So that means our total V dc dt is set to 0. So we're not changing the concentration of this pollutant in the lake over time, even if we're changing it in the stream flowing through it, or the water flowing through it. Okay, let's see, what else do we have? We have a couple flow rates, some concentrations. So it said completely mixed, we talked about that. It also noted that Q is constant, essentially, or there's a balance of it. Okay, I think that's probably all we need to know in order to give this a shot. So the question is asking us, find the concentration leaving the lake. Okay, so, well, we need to know the flow rate leaving the lake. That's going to be pretty obvious. We're going to add the two together, the stream plus the sewer. Well, I'll call this, it says W. And then the real question is, what is Cm? Okay, so just like last time, I will begin a little bit setting it up. I'll delay myself to give you some time to think about it and challenge yourself to figure this problem out. Bless you. You guys are allergic to mass balances. All right, so one thing that might give you a hiccup here is that when we do our reaction, it's on some concentration C, but what is that C? Well, that's going to be the concentration that is inside the lake. And if you stop and think about it, we've got a CS that's coming in, a CW that's coming in, a CM that's going out, but what is C? Well, C that's coming out is exactly what's in here because we're well mixed. So we're going to say this is CM. So hopefully you got to this point at least, and then there was a chance you had some confusion there. All right, I'll give you 2 more minutes to try to get an answer here. All right, so I'll join you here. So we have our equation at steady state. We say 0 equals the 2 inputs, that's QS times CS plus QW times CW, so 2 input streams. Each of these are an input rate. We're just going to sum all the inputs. Minus all the outputs, there's just one output rate, QMCM. We're going to try to solve for that CM. We already talked about QM. And then the reaction term will be in that volume of this lake. It's a decay reaction, so we have a minus volume times the rate constant times, again, the Cm that we're trying to solve for, to the 1 power. Now, earlier I mentioned K. I went ahead and converted because of all of our flow rates are in seconds. I figured we might as well put this into seconds as well. So I took the 0.2 per day, multiplied that by 1 day per 86,400 seconds. And that turns out, that's the number of seconds in a day. So that becomes 2.31 times 10 to the minus 6 per second. Okay, so with all of that, we can put in some numbers here. Should be able to solve. In fact, I'll go ahead and simplify a little bit for Cm and then put in the numbers. So we'll go ahead and add these two terms to both sides and get Qm Cm minus VKCm equal to the inputs minus the output, or excuse me, equal to the inputs essentially. QSCS plus QW CW. Of course, we have numbers for many of these. I just want to simplify a little bit before we go there and solve that way. So Cm times Qm minus Vk equals QSCS plus QW CW. All right. So then that should give us an equation that looks like this. Cm equal to QSCS plus QW CW divided by Q mixed minus V times K. And if we put all of this in seconds, like I did with the rate constant, we should be able to put in all of these numbers. And what we will find is for the flow rates, the cubic, we'll end up with cubic meters, but those should all cancel because we have cubic meters in every term. And then the seconds is where it matters, right? The seconds, cubic meters per second here, assuming those are good, and Qm is also in cubic meters per second, which it is, that's how we have it, then we're okay. Then everything matches. We will be left with, the remaining terms will be the milligrams per liter. So we didn't have to convert the liters to cubic meters because we have cubic meters per second here, cubic meters per second here. Those will cancel with the ones on the denominator. Yeah, question?
Is that minus sign supposed to be at first?
On the bottom, let's see. So yes, it should be. So excuse me. So I needed to add both of these terms, and I added them as if they were in brackets. Thank you. Okay. So with that, you can take it from a calculator. I'm going to go ahead and do that except on Excel. So we will solve for Cm here and say that's going to be equal to Qs times Cs plus QW times CW all that divided by Qm plus the volume, which was, it's essentially 10 to the 7th, it's 10 times 10 to the 6th, cubic meters, times our K in per second. Okay, so then we should get a value of 3.49 milligrams per liter. And we can double check for ourselves that this is a reasonable number. If we take a look at the problem, we have 100 milligrams per liter coming in at one point. That's the high concentration. 10 milligrams per liter coming in the other point, and a decay reaction drawing all of this downward. So imagining that it cannot be above really this number, 10 milligrams per liter, it is somewhere below that. I mean, I guess it could be if it was very, very little reaction happening, but we kind of expect that it's doing something. So it's probably lower than that, but not too far from it. That looks pretty good to me. So that would be our answer. Does that make sense? Any questions? Now, one thing you'll notice is sometimes especially while I'm talking about it, I'll miss the negative sign. So one thing I'll tell you on exams is one thing how I grade is if that's the only problem you made, I'm a little sympathetic because I kind of make those problems sometimes too. And thank you for catching them. Keeps us both awake. So if it's something like that, you'll find typically that's the way I treat that is like 1 point off. Okay, you made a mistake, but it's not what I really am testing you on, assuming it's not an egregious mistake. Okay. So last thing I want to talk about for the reactions and stuff before we move on to the chemistry review is the fact that we can derive a rate constant from some data. This is a pretty useful thing, and I'm just going to go pretty quickly through it. You've done this before. You just haven't looked at it in this way. So you've done a line of best fit. So if we have a zero order reaction and we have something changing and we get some data points that look something like this, you would be able to draw a line of best fit, use Excel, maybe a graphing calculator, figure that out, and get it in a y equals mx plus b form. It turns out that we can, if we're thoughtful about it, we can take some batch kinetics and treat this dc per dt as a slope. And we can do this for different reaction orders if we linearize the y-axis appropriately. And we'll have some way to find our m, the slope, essentially is k. So if we find the change over time for a zero order equation where we are plotting some change in c per time, well, it turns out that, like we said, v dc dt for a zero order, let's say, okay, yeah, sorry, I didn't realize I skipped the page. One moment. Okay, for a zero order decay, in a batch, it's very convenient to solve for kinetics, meaning the rate constant kind of stuff, in a batch scenario because the only thing affecting it is the reaction. So this is going to be a negative k times c to the 0 power. So that dc dt, if we take the derivative of this plot, we end up with this slope. Okay? So it's very straightforward. If we have some data and we can take a line of best fit, then we can solve for essentially y equals mx. Of course, we might have a plus b, but that's not going to really matter for what we're solving for. So in this case, that would be a negative mx. We can tag on the b there, sure, and then c naught is b. Okay? So we can solve for that, and it's pretty straightforward. If we had a first order decay, we can linearize it by taking the natural log, because if you remember, our dc dt, our derivation, gave us this c over c naught equals e to the minus kt, and we ended up saying, well, if we take the natural log of c over c naught, that would be equal to negative kt. Or maybe we didn't say that, but you can see that we could have. In fact, when we were deriving this equation, this was a step along the way. So if we just simply take the natural log and plot it this way, we would start at a value of 0 and go negative. And that'll make sense if you look at the natural log of 0, or excuse me, the natural log of 1 is 0. And then maybe we have some data. If it's a first order reaction, this will linearize it. And we plot that, and we get our line of best fit. And hey, that's our k. Because again, we have y equals negative mx. In this case, b is 0, so that's very handy. So I just wanted to point out the fact that we can use kinetics to find K. We can even use, let's say, the same concept. If we know something about, for example, the half-life, we can solve for K, given what would happen in a batch. So the half-life would look like C over C naught equals 1 over 2. That's the half-life. And so if we know the half-life of something, we can usually find C if it's, let's say, a first-order reaction. Okay? You'll actually, I think we have a homework problem on that. So you'll see that in action, and we'll go through that as an example there. So a little aside here. Okay, mostly I wanted to introduce you to the fact that we can find information about our rate constants based on observed data using these same exact principles and just a little bit of thought about how we are plotting or how we are looking at the data. All right? Mostly I want you to know how to construct these mass balances and then use them. Okay, so now on to your favorite topic. We'll get to some chemistry. All right, so for sure this will be a review for many of you. Some of it will be a review for all of you. Some of you will have some new parts here for sure. So let's just dive right in. So simple level, with our periodic table, just want to remind you that we have a few numbers here to take a look at. So here's oxygen. Often when we are talking about oxygen, we talk about the oxygen we breathe. That's that's molecular oxygen, O2, 2 oxygens. Oxygen itself, as an atom, has this number as its atomic mass unit. This number, I think that's the, let's see, forget the specific. That's the element number, probably, something like that. That just means how many protons it has. And each separate element is defined by how many protons it has. Now, many times they have neutrons that are, they each weigh 1 atomic mass unit, a proton and a neutron, and often some electrons. Don't worry too much about all that. This is the atomic mass number, or excuse me, this is atomic weight. And this is going to be essentially telling us how many grams per mole there are. So oxygen, just the atom, is approximately 16 grams for every mole, which means for the oxygen molecule that we breathe, it's typically 32 grams per mole. Now, it turns out ozone is O3, and I have all this written down here too. So ozone would be 48 grams per mole because it's 16 times 3. If you're interested, that slight deviation does have to do with what we call isotopes. Sometimes there's different numbers of neutrons. Occasionally you'll have an oxygen atom that has 8 protons and only 7 neutrons instead of the typical 8, which would get us to 16. So we average it out based on the typical amount in Earth, how many are like that. Don't worry about that. Not at all. Just that's where it comes from. That's why we have a strange decimal place, in case you care. Electrons, by the way, weigh almost nothing, so we don't really see their effect in here. Okay, so we know what to do with the periodic table, right? This is all hopefully review, and just keep in mind that the way we are going to use a molecule or use this nomenclature, the little subscript, that's saying there are that many number of these atoms within that molecule or that part of the molecule. If we had 2 out here, O3, that means we have 2 molecules of ozone. Okay? And there are 6 total oxygen atoms in 2 molecules of ozone. Okay, hopefully that's very straightforward. Just remember that's how this is working, because then if we have 2 H2O, that means we have 4 atoms of hydrogen and 2 atoms of oxygen in 2 water molecules. Okay? So Just want to make sure that's all clear. Now, some atoms tend to have a charge of some sort when they're in water. We'll call these ions. And some molecules can have charges as well. I want you to be familiar with some simple ones, some standard ones. And in the first homework, the first page is optional, so if you're already a chemistry whiz, you can skip that. And it's going to have you, in part, just refresh your memory on some of these polyatomic ions and what their typical charges are. All right, so for any of you that have taken some environmental engineering classes or chemical engineering classes, I hope that you would know if I say sulfate, it's SO42 minus. Boom, you just know that. If not, you should study this and make sure you're there. If it's been 5 years since you've looked at chemistry, here's a reminder. There are things called polyatomic ions, that's just a fancy word for it, that have a typical charge, and it would be good for you to recognize in case you see it on a homework or an exam. You'll be like, oh, okay, yeah, this should have a such and such a charge. So, for example, phosphate has a 3 minus charge, PO4 3 minus, and sometimes we can add a proton to some of these. And that's going to be relating to our pH concepts. Some of them won't really do that too much. For example, nitrate, NO3 minus, nitrite, NO2 minus. So there are many of these. The OCl minus, this will be our chlorine with HOCl with no minus. So note that H plus is a 1 charge, right? So I want you to be generally familiar. It would be very helpful for you to memorize at least these few at the top, these ions, maybe even add magnesium here. These are pretty standard ones, and they're not going to change. There are some exception ones where you could have iron, for example, in 2+ or in 3+, depending on what we call its oxidation state. Don't worry too much about that. We'll talk a little bit about it here and there, but I'm really not going in too much depth for you. See my other class if you want some more depth on chemistry. All right, so I want you to be familiar with a few of these and comfortable enough to be like, oh, okay, this one, it appears on the left side of the periodic table over here with hydrogen. It's probably going to be positive charge. Okay. Oh, it's over here on the right side. The very right, these are the noble gases, and then we have the halides, the halogens, which are a -1. So some familiarity with how the periodic table is working will do you well. All right. More importantly than all of that, I want you to make sure you understand and can do some basic stoichiometry and calculating from some moles to mass back and forth. And recognize that sometimes we'll have to go from mass to moles, then moles back to mass. This is relevant, for example, and here is an example, if we wanted to burn some gasoline. We might say, okay, I have a gallon of gasoline that weighs some amount of pounds or kilograms or whatever you want to say. How much mass of CO2 or of water will that produce? And if you're wanting to weigh it in the first place and then weigh your product, well, you need to go from mass to moles to understand the reaction, and then back to mass so that you can understand what that means. All right, so that's your challenge. You have to be able to convert from pounds to dozens back to pounds. Okay? Remember, dozens is the non-scary way to say moles. It's just a different number in there. So, given all that, the stoichiometry, that's the fancy word that means the number ratio. Remember my stupid analogy of egging a car, right? How many eggs per car? How many moles of this per moles of that are going to react in order to get our product? We have to go through the numeric exchange because mass doesn't always do it, right? We can't always compare mass directly. So, all chemical reactions we deal with are on this numeric basis. Occasionally we'll find cases where we can simplify and ignore this, or it's already built into our calculations. But for the purposes of our class, let's make sure we are dealing with our chemical reactions on numeric basis. So stoichiometry means how many molecules of methane will react with how many molecules of oxygen to form some number of CO2 and some number of water. You should be able to fill in these question marks. And I'm going to walk you through this one and then give you a challenge to solve a problem. So the reason I say you should be able to is this is a mass balance, essentially. And it's just a matter of understanding how to set up and solve for these pieces. So when we encounter a problem like this, a simple way to approach is to take one piece on the left that has, let's say the carbon is a typical way to start. Just assign it 1 and we can change it later if we have to. We'll just correct everything after. So let's start on the carbon basis. If there's 1 carbon on the left, that means the thing on the right has to have 1 carbon. So we start with the thing that there's few of them on each side. And usually we're dealing with something like carbon where it's like that's our basis. That's what we're really concerned about. We're measuring by. So 1 carbon on the left goes to 1 carbon on the right. Now we have also hydrogen in 1 place on the left and 1 place on the right. So let's balance those next. Because oxygen is on 2 places on the right and 1 on the left. So let's save that one for last. So hydrogen here, we've got 4 on the left. Let's make it to be 4 on the right. So 1 over here to 2 waters over here. We'll balance that. And then we check the oxygens. Are they balanced? Or how do we balance them, rather? So we have 2 oxygen molecules here. Atoms. 2 oxygen atoms here. And we have 2 here. Right? So that's 4 total. That means we could have 2 molecules of O2 to solve that. All right. I'm going to move on. If that's not clear, get with somebody to help or get with me to help you. You should know that. All right. So if we take butane, which is C4H10, here's an example that you could solve. What is the mass of CO2 produced if you burn 100 grams of butane and it's fully oxidized? I'm just thinking about the time. I don't have enough time to do the whole chemistry refresher here, so we'll do a little bit of it on Tuesday. But I'll give you 3 minutes to attempt this problem. You probably won't get all the way, and then I'll finish it with you. The atomic weight for hydrogen is approximately 1, by the way. So as you go through that, make sure you know that. All right, so you can see how I've set this up for you, and I'm just going to go ahead through it. Hopefully that gave you enough time to think about it. First thing I did was I wrote down the molecular weights for butane and CO2. So for butane, I took 4 carbons at 12 atomic mass units, so 12 grams per mole each, and 10 hydrogens, and that's why I wrote up here that it's approximately 1 for each. So that'll be 4 times 12 is 48 plus 10 is 58 grams per mole for butane. And for CO2, we have 1 carbon at 12 and 2 oxygens at pretty much 16. So that'll be 12 plus 32 is 44. All right, so those are my molecular weights. And then I did the stoichiometric balance. And you see, I went ahead with my approach again, starting with 1 butane, saying, okay, well, there's 4 carbons, so I have to have 4 CO2s. And then I did the oxygen balance, or excuse me, the hydrogen balance, and I found, okay, 10 on the left will give me 5 times 2 for 10 on the right. And then when I did the oxygen balance, I needed 9/2 of O2. Now, it doesn't matter to me which way you go about this. Some people prefer whole numbers, and you must have whole numbers because you can't have half a molecule. That's fine. You multiply everything by 2, and you get 2, 9, 8, 10. But what really matters is the ratio between butane and CO2. And that's a 1-to-4 ratio no matter how you slice it. So given that you have 4 carbons in butane and 1 carbon in CO2, that's how it's going to balance. This is really the part that matters, the ratio between these two. So if you look at this in terms of a units problem, you'll find that all you have to do is make sure that no matter how you're dealing with the mass, no matter how confused you get, make sure that you are doing unit conversions properly. So we will go from 100 grams of butane, I'm going to abbreviate that as BUT, to convert that into moles of butane, we need the molecular weight. So we're going to multiply this by its molecular weight, but the units need to cancel, so it has to be 1 mole butane per 58 grams of butane. So I just flipped it to make that work out. That'll give us some number, and then we can convert from moles of butane into moles of CO2 by using this conversion. Okay, so we have moles of butane on top, so we're going to flip that and say, okay, now we need 4 moles of CO2 per 1 mole of butane. So now, if we track our units, we will have canceled everything except moles of CO2. And I might as well go ahead one step further and put this back into grams of CO2 and say this times 44 grams of CO2 per 1 mole of CO2. And then I did this all in one string. You certainly don't have to do it in one string. I'm kind of making it a little quick here. But this might be a nice way to do it so you can see and make sure that you've converted from one unit to the next all the way to the point where you're in grams of CO2. All right? So if we do this, anybody have a calculator and do that handy for me? Are you going to make me do it in Excel? 303? All right. That sounds correct to me. 303 grams CO2 for this reaction. Okay, and it kind of makes sense that should probably be a heavier number because hydrogen doesn't weigh much, and in butane we have hydrogens, and we're replacing that with oxygens for every carbon, which is heavier. So that looks about right to me, and I'm pretty sure that's exactly what we've had. Question? Say that again? Sorry, say that again? Which part?
That should be 13 halves and 13 instead of 9 and 9 halves.
Okay. It turns out that even though I made a mistake there, the problem still adds up the same because it was the ratio between the carbons that mattered. Okay, so good catch. Thank you, and I apologize for the mistakes. But the ratio mattered. All right, we will do pH and equilibrium next time and get into drinking water. So see you on Tuesday.